So we have to show the following theorem. So this was, I think, the maximum principle for our notion of subsolution. So let omega be an open set connected. Let upper semi-continuous. We always assume that that is not identically minus infinity. Okay, so let U be upper semi-continuous. Suppose that the upper semi-continuous, and suppose that for any x in omega there exists a positive number such that U of x is less than or equal to V x r in 0 r of x. If 0 in omega is a maximum point of U, then U of x not equal max omega. Then U is constant. Okay, so this is a sort of strong form of the maximum principle, because remember that each time we discussed the maximum principle, we said, okay, the maximum is attained for a subharmonic function like this, no? So this is maximum say strong maximum principle for subharmonic we said, okay, the maximum is attained at the boundary, but we cannot exclude that it is also attained inside. This could not be excluded. Under the assumption that now omega, here omega is not necessarily bounded, by the way, but it is connected. So this says that unless you are constant, if you are not constant, there cannot be interior maxima. Okay, unless either you are constant, but if U is not identically constant, then there cannot be interior maxima. Okay, so the proof of this strong, so in this sense is strong. And the proof is as follows. So define two subsets Okay. Then what do we have? Then B is open. Because U is upper semi-continuous. A also is non-empty. So supposing that, okay, the intersection is empty, omega. So what it is enough essentially to show that A is open. Okay.
Okay.
So it is. We need to show because you suppose that it is not. You suppose it is not identically constant. Then you consider A and B. Then B is non-empty also. But if you show that A and B are open, they cover the whole omega and you get a contradiction, right? So suppose not identically constant. You need to show, to reach a contradiction, since omega is connected, contradiction A is open. Okay, is this clear up to now? So I'm supposing it is not identically constant. Then I consider these two sets. They are disjoint by definition. By definition, B is open because U is upper semi-continuous. Upper semi-continuous. U, B is also non-empty because U is not identically constant. A is non-empty because it contains x naught by assumption. U x naught is equal to M. So if we show that also A is open, then we have a contradiction. Okay. So take, okay, we take a point x into A, and we consider the R of x. So what do we have? We have that U of x is less than or equal than V capital U x R for any R in 0 R of x. So is the integral x and x in A. We want to show that there is a neighborhood in which we still have necessarily, okay, But u in BR of x is less than or equal than m. BR of x is less than or equal than m. Yes. So this is m. Value. U is less than or equal than m. BR. And so this, I think, shows that necessarily
U is almost constant.
U must be, must be constant. Since U must be equal to constant BR of x, no? So m is the maximum, x is in A. Here U is everywhere less than or equal than m. So in order to have the mean value exactly equal to m, we must everywhere must have this. Not almost everywhere, but also everywhere. Remember that here U is defined everywhere. Everywhere. So this you can do by contradiction if you want. If you're not convinced, you can try to do this. Indeed, suppose by contradiction that this is not equivalently equal. Not identical equal to m, then you have to use
Upper continuity, semi-continuity maybe.
Exactly.
This is,
Exactly. Yes. Then use the upper semi-continuity to get the contradiction. Indeed. So this shows that this okay. So this shows the theorem. Strong version of the maximum principle for sub-solutions. Okay, as a corollary now, we can prove the weak maximum principle, yes, maximum principle which is a strong improvement of what we have already done using the PDE. Proving our previous weak maximum principle that we made for classical subharmonic functions. Okay, so let's see this corollary. Let omega be open and bounded. Remember that by experience, we know that if we don't put boundedness, then there are problems in the comparison and maximum principle. So, so now, previous case was that assumption. Now we take this. Let U the upper semi-continuous and such that still we have the same mean value, volume mean value inequality, even for possibly radii smaller than the distance, so such that, again, I'm tacitly assuming that it is not minus infinity identically minus infinity in a connected component, say, of omega, such that for any x in omega, r of x in 0 d omega x, such that u of x less than or equal than suppose im sup y in omega y less than or equal to 0 for any x boundary, then of x less than or equal to 0. Okay, so this is the improvement. Okay, so before doing the proof, I would like to give you an home exercise. Home. Quick comparison. Principle subharmonic and superharmonic functions. So let U harmonic. So let omega be bounded. Let U be subharmonic. Omega, let V superharmonic. Suppose that sup okay, so this is the theorem. So this is the theorem that we want to show. Okay, define So we give the following definition. We introduce the function u bar. Now u bar, I ask you, is u bar upper semi-continuous? Yes or not?
Yes.
Perfect. Yes, it is clearly by definition upper semi-continuous.
Yes.
On omega bar. Okay, now omega bar is compact. Since omega is bounded, bar is compact. And therefore, u bar, being upper semi-continuous on a compact set, admits maximum value. Maximum value on omega bar. So let M the max on omega bar, which is u bar of some x naught. Okay. Now there are two cases. Possibilities, x naught is on the boundary or x naught is
Inside.
So
if it's inside, then the function is constant in that component, that connected component. So we always can find such x naught in the boundary. Namely, then u is the constant in full path component, connected component. So in particular, it's also equals to m in the boundary of that path component. So that connected component. So we always can find x naught in the boundary.
Let me see if I have understood. I think you are completely correct, as usual. But let me see. There are two cases, as I was saying. Let's see if we can make clear what you were saying. There are two cases. Case one, naught is on the boundary. In that case, we have m is the maximum value reached at x naught. Sorry, m is the maximum value reached at x naught. X naught is on the boundary. U bar is upper semi-continuous. So this is always less than or equal to the lim sup less than or equal to the lim sup y omega y converges to omega.
I think it's just equal by the definition.
Equal, yes. But less than or equal is not wrong, but yes,
yes.
Equal to y, which by assumption, I have erased? No. Yes. By assumption is less than or equal than 0. Equal. Less than or equal than 0. So the maximal value is less than or equal than 0, which implies that u is less than or equal than 0. Yeah. Right? Because the maximum value is less than or equal than 0, and so. Is this clear? Yeah. Second case. Not is inside. He was suggesting to consider the connected component containing of omega containing x naught by the previous theorem we get that since omega prime is connected, we get that u is identically constant on omega prime. No? And we also have that so u of x naught, so u is identically equal, so therefore the limit, so u is equal to m on the boundary of omega prime, right? The boundary of omega prime is contained in the boundary. Okay, so m is equal to the limit as u of x, y, less than or equal than the lim sup if we want. Less than, because any point on the boundary of omega prime where I know that u is equal to m is a point on the boundary of omega, and on the boundary of omega I know that we have this assumption. Okay. And therefore m is less than or equal than 0, and the same conclusion as before. I think this is more or less what you were saying, right?
Yes, yes. Yes.
So this gives us an interesting comparison result between subharmonic and superharmonic functions, and we are not using anymore the Laplacian or the gradient at the maximum point. We are just doing this. So now let me do a remark. So the question is if we can we slightly change the A remark or maybe an exercise, if you want, is the following. Maybe this I can leave it to you. So home. Is it possible to replace this assumption with I'm asking if the weak maximum principle still holds when I put sort of a less restrictive assumption, the lim-inf instead of the lim-sup.
I think no. But if we change the inequality also, then we can the opposite.
No,
maybe.
okay, that's clear for superharmonic.
Yes.
No, but for subharmonic.
Then the new function u bar is not after same continuous function in omega bar. If
No, yes, of course the proof does not work as
yes.
that's clear. But do you have yes, no, I have understood what we are saying. The proof does not work. I definitely agree. But do you have a counterexample? This is the point. I mean, can you exhibit a function which is can you exhibit a function? So what do we know about this function here, the Poisson kernel with singularity at y0 on the boundary of a ball? What do we know about this function here? This function, remember the expression maybe, no? This function, which sign has this function inside? This function, first of all, is harmonic inside.
Yes. It's harmonic, so it's
harmonic and
subharmonic.
And the sign inside is how? Negative, positive, zero inside.
Inside positive.
Positive. And what do we know about the lim-inf at all points on the boundary? We discussed last time, do you remember that we saw that the limit here is 0. Then here there is a singular point where the lim-sup was plus
infinity.
The lim-inf was
0.
So this is a counterexample. But inside it is positive, okay? So we have to be really very careful about, we cannot exclude single points in this argument. It's fundamental that everything is defined everywhere, at all points. So this gives, but think about this. This is an home exercise if you want, okay? Fine. Now, in the way for solving the Dirichlet problem with the Perron method, we need some other result. So we need to characterize subharmonic functions and the same superharmonic, evidently, with other ways. I try now to write a statement, try to condense the ways we need. So, characterization. So let omega be a bounded open set. Usual, almost usual. Let U minus infinity plus infinity be upper semi-continuous in omega. As usual, we suppose that it is not identical in minus infinity, etc., etc. The following conditions are equivalent. For any x in omega, u of x less than or equal u as u r for any r d omega x, which means the surface mean value inequality holds at any point. For any x in omega, u of x is less than or equal than the volume value inequality. X in omega surface mean value inequality possibly with a distance less than the distance from the omega, from the boundary of omega. Let me write down here the implications because otherwise 1, 5, for any ball open ball solves this is the list. I think I have forgotten. Maybe I have not forgotten, but I have not written completely correctly because I have to give to U is a sub-solution, so let's see this. Maybe this is okay. Okay. Let's see if these statements are correct during the proof. So, first of all, let me comment about this, then we'll try to prove it. So we will discover if the statements are correct or not. But first of all, this is easy to say. I mean, if we take balls with some radius depending on x, or balls radius up to excluded d omega of x, this is equivalent to this, and this is the equivalent to this. No? And it is clear that 3 implies 1, that 1 implies 3, and 2 implies 4. Now this is clear. 1 implies 3, and 2 implies 4 is clear. And it is also clear that 6 implies 5. No? Now, which is the advantage? Now, this is a formulation related to the notion of subsolution, of course. This formulation, 1, 2, 3, and 4, whatever, if you have R of x or not, in any case, you need the surface mean value or the volume mean value, which is something which is strongly related to the minus Laplacian, the operator. This instead, 0.6 or 5, sorry, 0.5 or 0.6 says something that seems to be that you can, you can use for other elliptic operators, in the sense that you are subharmonic if each time you have a smooth superharmonic function that on the boundary is larger or equal than u, then the smooth superharmonic function must be larger or equal than u inside. The smooth superharmonic function must be larger or equal than u inside. So this is a sort of saying that you can test your inequality for u just against smooth objects locally in a ball. And here, of course, you don't have any kind, in principle, of volume in value formula. So in principle, you could say, okay, if this theorem is true, then for me, say, 6 is the definition of subharmonic function. But then if 6 is a definition of a subharmonic function, I don't need anymore to speak about surface and volume in value formula. I just say, if as soon as I have a smooth supersolution larger or equal than u on the boundary, this smooth supersolution must be larger or equal than u inside. Supersolution of my operator. Okay, so in this sense, maybe 5 and 6, if the theorem is true, seem to be adaptable to more general operators. Okay, now let's see the various implications. Maybe we could try to show that implies 2. Okay. Or maybe implies 2. Maybe not 3 implies 2, sorry. Because one of them can be obtained by integration and the other by differentiation, no? So now I have to see which is the best. Let me write, before writing the implication, let me write, so I have the 1 over omega n rho n rho y dy. Write it as 1 over y dh 1 y dr. So this is 1 over omega n rho to the n. What? This is S of u x r multiplied by sigma n minus 1 r to the n minus 1. Times r to the n minus 1, the mean value. So supposing that we have a surface mean value formula, say 1 implies 2, maybe I'm doing. So if I have a surface mean value formula, less than or equal than 1 over omega n rho to the n sigma n minus 1 of x integral from 0 to rho r n minus 1 dr. So this is the volume formula. I'm getting the correct expression. U was below. So this is the volume with value formula. Correct? Huh? Can you help me? Is it correct?
Yes, it's correct.
It's correct. So this should give me, as usual, my u of x, I hope, no?
Yes, it's n sigma n minus 1 or omega n, it's equal 1. It
So
equals
it
1.
should cancel with this. And,
yes.
So this says that we have shown that if the surface mean value formula holds, then the volume mean value formula holds. So this is 1 implies, is 3, no, is 1 implies 2.
2.
1 implies 2. Okay, And the same argument is 3 implies 4. Same proof, okay? Now, let me see if we can do, now we have to go here, so maybe all, maybe we can try to prove 6, starting from 1 or 2, I think. Or no, in order to so we can prove 6 here in my notes. I write 6 as a consequence of 4, if 4 is this, I don't know. So 4 implies, let's try to prove this, okay? This should be an easy consequence of our weight comparison principle. Okay, so so 4 now is the volume in value formula in local form, say, with the R of x. And I pretend to prove this, which is the stronger form, because A is just an open set, bounded. So let A open set, let V be so let V be as in 6, let V be such that super harmonic want to show this. Want to show this, and this should be a consequence. The only way to get this is to make a comparison argument, weak comparison principle between what? Between a super solution and a sub-solution, no? So this seems to be rather natural that we can do, hopefully, no? So we define the difference. U minus V. So what do we know about U minus V? So first of all, U is upper semi-continuous, V is smooth, A here. V is smooth, continuous. So this is upper semi-continuous. In addition, from this, sup y in A, y should be less than or equal, then less, because it is, I mean, it is what is, so V is smooth. So this is the limit, sorry, it's the lim sup y in A, y converges to x of U of y minus the limit y in x of V of y, right? Because this is smooth. This is less than or equal than what? This is less than or equal than, so U Yes, this is less than or equal than u of x, because u is upper semi-continuous at every point, in particular points on the boundary of A. And this instead equal to v of x, because as I say, sorry, this is less than or equal than u of x, but this is equal to v of x. So at the end, less than or equal than 0 by assumption here.
Yes, yes.
But then by the weak comparison, by the weak maximum principle, we can say that W is less than or equal than 0 in A, which is exactly what we want to show. No?
Yes, but we also have to check one thing, and it's also clear. Just volume mean value for using big maximum principle. Volume mean value formula for W.
I have not understood. I mean, in order to pass from the inequality on the boundary, for all points on the boundary, no?
Yes, we also should check one thing. Namely, W also satisfies volume mean value formula. Namely,
In order to pass to this inequality inside.
yes, yes.
And so this is equivalent to this, no? I want to show 6, no? Do you remember? I want to show 6. So I have to show that this inequality holds for any v, etc., etc. Way is to pass through the weak comparison principle. Now, the difficult part of the proof, I mean, is unfortunately this is not closed. Is that 5 implies one of these. Well, maybe it's better to. Let me see. If I prove that phi implies 1, is closed now. 1, 3, 4. 1, 3, 4. Yes, I think it's closed, no? Because 1 implies 3, which implies 4, which implies 6, 5, 1, 2. Seems to me that what remains is 5 imply 1, no? Right?
Yes, it's enough.
So it remains to show so if we show that we are able to, if the comparison with smooth super solution on balls implies this sort of surface mean value formula, then the proof is concluded. So let me erase because this is more difficult. Okay, the idea is, so suppose first, so we want to show that 5 implies 1. We don't know about the continuity of U. Let's suppose first that U is continuous. So the idea is, first idea, suppose U is continuous. Then the second step will be just only upper semi-continuous, try to approximate it from above by a sequence, pointwise by a sequence of continuous functions. Next step, approximate. So we concentrate here in this case, approximate by decreasing sequence suitable, sequence of at least on a compact set. Okay, so suppose first that U is continuous. Then I'm able to compare, so maybe then fix a ball. Yes, fix X and the radius. So here I have a ball. Inside this ball, I can solve. I can consider this. Consider the following problem. Minus Laplacian of V equals 0 in Rx, V equal U Rx. Okay, now what do we know about this problem here? So U now is continuous by assumption. Now U is continuous. Continuous in particular here. Right? So if you remember our long discussion, we were able to solve the Dirichlet problem for continuous boundary condition in a unique way in this class. And we indicated by the solution in some way. So we have a unique solution, which I think we have indicated in some way, maybe P. P no Vx, Vz. I don't remember if this was the notation. Maybe yes, no? Poisson formula, no? P, and this was the boundary condition, no? Do you remember? We used, I think, PG, PG of this, no? I don't know. I don't know. Do you agree with this notation? PG. Now G is U restricted to the boundary of BR.
Yes, agree. Absolutely.
I want to be consistent with the notation. I don't remember exactly, but I think that I use exactly this. No, I'm not sure, but please check. So in any case, doesn't matter this very much because this has an explicit expression, more or less. Actually, it is explicit. So what is it? So it is integral on the boundary of Brx. No? You have to be careful about the, here we have the boundary condition. Then we have 1 divided by x z minus y to the n. Here we have r squared minus z squared divided by sigma n minus 1 r, I hope. Okay? Correct? Can you check? So we are taking this solution. We know that this solution, previous theory, last lectures, long story.
It's just we put Poisson kernel, we found so,
Yeah,
explicit formula via Poisson kernel.
It's just the Poisson kernel. The problem is not to make mistakes with the variable, because there is x is the center of the ball, y is on the boundary, and z is inside. No? So this is the point. So y is here, z is here. Okay, 3 points. The only. Okay, this should be correct. So what do we know about our assumption 5? Our assumption 5 is saying that as soon as we have a smooth solution or super solution of this, then this must be true. Okay? So assumption 5 says that V must be larger or equal than U. Okay? Assumption 5 implies that V must be larger or equal than U in the R. So let's evaluate this inequality at the center of at X. In particular, V of x must be larger, which is what? Now I am taking as z equal. Oh no, but there is a translation here. I think there is a mistake. There is a, so in place of y there is y minus x. Of all. Then I think that in place of z there is z minus x, no? Sorry. I forgot. This was the formula for the origin. No? Okay. What's happening if I take z equal x? In particular, at the center, taking z equal x, z equal x is inside, so at the point x, this must be larger or equal than this. So v of x, which is something, must be larger or equal than u of x. At the center, this is 0, so we get r squared divided by sigma n minus 1 r. This is just y.
I think it may be x minus y or something. There is sign problem.
Is the same problem?
Sign.
Z minus,
X
yeah.
minus y or because 2x minus y.
Yes, you're right. You're right. Thank you. Of course. So let me repeat it. So if I take z equal x, this is 0. So this is r squared divided by sigma n minus 1r. This z minus x is equal to 0. So this is y to the n. But y is on the boundary, so this denominator is constantly equal to r to the n. R squared coupled with this becomes r to the n plus 1 of y dy, which is exactly s u x r. So interestingly enough, we have shown that u satisfies right? So d of x must be larger or equal than u of x. Therefore, u of x is less than or equal s of u x r, which is assumption I, which is the thesis I. Okay? So this shows that at least under the assumption that u is continuous, we can solve. Remember that up to now we were able to solve uniquely with our Poisson formula for a continuous boundary condition. Do you agree with this up to now?
Yes, yes. For generalization, maybe I think we can use monotone convergence theorem just.
Yeah, I think so. Let's see. Let's see. So if Rahama agrees, Rahama?
Yes.
Clear?
Yes.
Perfect. So now what remains to show is when u is just upper semi-continuous. So next step. Now, so suppose u just upper semi-continuous. Now take a sequence that u be just upper semi-continuous. And now we take a sequence, as I said, of so fix x, fix r, fix x, fix r, and take a sequence. Let me call them, I don't know, Vj. A sequence maybe Uj from BR closure X into R, continuous, decreasing, so any upper semi-continuous function on the closure of the ball, Brx, is pointwise limit of a decreasing function. Did you find this? This is not easy. Maybe I can give you a hint, I don't know, about this. Let me see. There is a very interesting expression related to the Yoshida transform about this. I prepared some exercise that now I don't have anymore. Something like, so if, say, Did you try to solve this, to find the sequence in general for a lower semi-continuous function or for an upper semi-continuous function? And maybe I can try to give you a hint for this before going on. So let's take, say, let us consider, for instance, J of Z something like soup. Something like this. Sorry, omega seems to be a function, a name for a variable, xi. Something like this, with the minus. We want to approximate instead, so here there is power 1, I think. Here there is a minus. J goes to plus infinity. When here there is power 2, for a lower semi-continuous function, you can approximate from below, I think. Then you have to exchange the sup with the inf and the plus with the minus. Something like this. I don't know the reference for this. I don't know, actually. Okay. In any case, let's try to go on. So there is this phantomatic sequence of continuous function pointwise converging from above, maybe given by this explicit expression. And then the idea is more or less to do the previous step, but not with u, but with uj now. Okay. So now we consider uj. Solving this. So this gives us, for any j, so we have uj, in particular uj is larger or equal than u, okay? Uj larger or equal than u. Then we solve, we take the harmonic function. Now uj is continuous, so we can apply our theory that we did last lectures now with the trace which is equal to uj on the boundary. And so we end up with a function vj now, which is in this class. Here it is p uj, which has this uj here. Okay. There is some silence in the.
No, we just obtain that surface mean value formula for each uj. Just what will happen if we just put get limit as j goes to infinity, because we have surface mean value formula for each vj, and they are
Exactly.
monotone sequence.
So first of all, u of x is less than or equal than u of j. No, for any x. No, x maybe x was the center of the ball. No, I don't know now the variables, but no. So no, x is the center of the ball. Okay, so u of x is less than or equal than uj of x. Okay. Now, for what we have seen before, this is less than or equal. Unfortunately, I have cancelled. S uj xr previous argument, no? We evaluate this at the center. We evaluate this at z equal x. And we do the previous argument with uj in place of u.
Yes, we pass to limit,
and then we pass
we
to the
can use
limit.
monotone convergence theorem for the integral.
Then by the monotone convergence theorem, we can apply the monotone convergence theorem because uj is larger or equal than u, and they are all integrable, etc., etc. So we get finally that u of x less than or equal x. So this concludes, I hope, also the various implications. And so let me point out once more that one of the notions of solutions that seems to me preferable is one of these two. And you have seen also that how, when I told you that, well, now we study the problem for the sphere, this seems to be a special case, I told. But in general, it's not so special because this helps a lot for going on and proving something for more general boundary conditions, more general domains, etc. This is a first hint that says how important is to just to be able to solve for balls and continuous boundary conditions. This is sort of bridge for going from this special case to much more general cases. So, and again, I stress the fact that this way of putting, now since we have this theorem proven, we could say, okay, for me, a super solution U is an upper semi-continuous function satisfying this. Or, for me, a super solution, a subharmonic function U, is an upper semi-continuous function satisfying this. This is, in some sense, maybe more flexible, because here, it's enough to change the operator and leave the same inequality hold. Change the operator, just an operator in divergence form, you could use this as a definition of a subsolution. Here instead, you need the surface mean value formula, and as soon as you change the operator, it's not clear that you have any kind of mean value formulas. Okay, now I leave you a home exercise. So let n larger or equal than 3 define bar of x of z y x in Rn, define g bar of x equal g of x of y is different from x plus infinity equal to x. Show set r of x. So our fundamental solution at the end was, we know, a singular at the singularity point, no? Was harmonic outside, singular at the singular point. But if we pretend to define it also at a singular point with the only possible reasonable value, which is this, then this remains superharmonic, no? Which is not, I mean, this function here, no? It's not really, say, concave, but extended like this. But still, I mean, is superharmonic. Superharmonic. Omega. Okay. That's it. So I think time is over, and thanks for the attention. And we will see on Thursday, I think, Thursday and Friday. Bye.
Thank you. Bye.
Thank you.